Avionics.
It's on now, whether you can hear me or not. It's a whole other thing. Yeah, I guess the first thing I have to say is that now for something completely different than anything I've seen so far today. So DDCI, my name is Gary Gilliland. I work for DDCI. We're a company that provides certifiable avionics operating systems for aircraft, so the commercial and military systems. It's all we do. So unlike many of our competitors in this industry who have, just RTOSs and RTOSs for various different types of flavors, we just deal with avionics. So everything's designed from requirements and all that from the ground up. So, a lot of the talks that I've been doing lately is how to deal with multicore. And when you look at the industry, what most people talk about is the interference and how to deal with all that. And if you take, now this is not designed to be able to see it completely, but this is a IMX8 ARM architecture that's up there. And you can see there's a lot of integration. There's a lot of stuff going on in this chip. And the real goal of these chips and what they're trying to accomplish is to get this high integration, high performance in a low power package. And that's all fine and good. But it targets a lot of markets that the safety critical markets don't care about. I mean, we need safe performance. We need our hardware to be as separate as possible so we can guarantee performance and that kind of thing. So this talk's going to talk about a little bit how do you deal with that. We do run on these architectures, the IMX, SV332, layer escape products from NXP, the Xirinx UltraScale, which was the last one we talked about. But, the effects of all this integration really shows up in your worst case execution time of your tasks. And so when you're trying to figure out what those are, what are the things that you want to look at? So, you ask people, what do you think about that? And unfortunately, although it's getting better, there's groups, Multicore for Aviation, which is kind of run by NXP, and the Army has started a Multicore lab and environment where they're trying to figure out what are the things we have to deal with and what do you want? In the Multicore for Aviation, they were asking, what can we build you that we can make money on that would help you? That make money on part is whether we get any footing there. But a lot of times, it comes down to one of the most interesting things is the shared cache. So the shared cache that's shared by all these processors can get dirty, and flushing and refilling and dealing with that can really affect your timing. And so, having multiple memory controllers is often nice, and then even private memory per core. Starts sounding like we're designing a multi-core system where all the cores are independent. Well, is that really what you want? That's the sign there. So from the FAA, the certifying authorities, FAA, EASA, JPL, or JAL, too many JPLs talked about this week. They've come up with the guidance for CAS 32. They call CAS 32A, which is basically a way to show how you're going to mitigate the multi-core issues that come up. So, and they've put it in a way that models DO-178 processes and plans and that kind of thing. So you start with your plans, your configurations, showing what interference channels you think you have, how you're going to mitigate those interference, and then software verification. Those are all really normal DO-178 things. how you're going to deal with error detection, handling, and safety nets. This part's normal. The safety net's kind of an interesting thing. It's like, okay, you have your design, you've created it, you know what you're going to do, you've tested it, but what if it doesn't work? What happens then? So safety nets is kind of something they added in there. So one of the things they don't address, and I find talking to people that when you get the idea of asymmetrical multiprocessing or symmetrical multiprocessing, you get a lot of definitions of what that means. One of the things that, to me, symmetrical multiprocessing means, at least in a Linux environment, is that threads can migrate from core to core. You have a scheduler, and it decides what to weight and balance and where to put stuff. And in an avionics system, that's not going to fly. We need to know. For one, we design the system so we know exactly what's going on all the time. So there's not this concept of trying to load balancing, because that shouldn't be happening. There's not dynamic capability happening in the system. So they basically say stay away from that. So you have autonomous, or threads are stuck on the particular core. And then the concept of hyperthreading, which is the idea that these cores have multiple threads of execution. So they have a main core and then another. Intel uses the term hyperthreading, but every core has this technology. PowerPCs will have it. And the problem with that is that it's inside the core. There's really no way to separate what it's doing or or to know what the interference between that is. So they recommend that you don't use that as well. So some of the guidance objectives, I just throw this up here just to realize that for DL178, there's various different levels of certification, DAL-A being the highest, DAL-E being the we don't care. And so the document CAS32 kind of goes through, and for each one of those objectives, you have to say how you're going to deal with all of these kind of things. So this is just a sample of some of the inputs to that. We have to, for some of our audits, we had to provide a response to all these CAS32 objectives that are listed there. And these are kind of beyond the DL178 processes for developing your operating system and all. Now you've got to also respond to CAS32. So this is kind of just some sample guidance here. So I pull back a little bit to show DIOS is a product. We compete in the marketplace for DL178 certifiable operating environments. You notice also in CAS32, it doesn't mention anything about having to use a hypervisor in order to run a multi-core operating system. And the key there is you have to satisfy the requirements, but there's multiple ways to do it. So you look at the DIOS architecture is a microkernel architecture, a pure microkernel. So the kernel is a module. The PAL, which most people would call the board support package, is the interface. Gives the kernel the information about the hardware that it's running on. The registry is something that basically through XML defines everything that's going on the system. Each partition that's up here, each connection, those are all predefined ahead of time in XML. And when the kernel boots up, reads the registry, assigns everything. So everything's predetermined, predestined. There's no dynamic capability of creating new partitions after the fact. The other unique thing about DIOS is all the device drivers are all done in user space. And the capability there, or the main reason, is that you only have to develop the interface to the requirements you have. If you put the device drivers in the kernel, then they have to be developed to the highest level of your kernel. So put them out in the user space, you don't have to do that. The kernel is a gatekeeper for interrupts and authentication for who has access to what devices and that kind of thing, but none of those are involved with the driver. And in today's hardware, there's very little hardware that you actually have to have supervisor privilege to program or to interact with. So it's very easy to do. It also makes device drivers just user applications, which it's not black magic anymore. Device drivers have been black magic for, few people in the organization can actually write a device driver, but it changes that. So it's a pretty good architecture. So what you want to accomplish with safety critical, basically from that document, is bound and control the interference patterns caused by the shared resources in your system, and then getting good value from adding those extra cores and that extra in that architecture. The solution that we provide, we have several different things. One we call memory pooling and cache partitioning. Another has to do with scheduling. And then we have some other performance enhancing features using Slack scheduling and some different things we'll talk about. I like to talk to this as it's a toolkit. When in a single core environment, the operating system can control pretty much anything going on because it knows what's running at any one period of time. In a multi-core, we're kind of lost. We don't know what's going on every core, so we have to just provide you the tools to be able to create a safe system in that environment. So we start talking about some of the things like cache, and specifically shared cache. That seems to be the area where things are growing. The stuff that's on core is usually really quick and reflushes and refills often. The shared cache is a little more of a problem. And left uncontrolled can cause huge performance hits. There's nothing, if you're not doing anything to perform it, no matter how many cores, they could all be using the same area of cache, depending on where the code ends up in memory and how that's mapped in. So you got to be careful and control that. Over the years, there's been various ways that people do that, from cache flushing at every context switch, which makes the performance variability go down, but it causes more overhead in the context switch. Disabling cache, which I've heard some of our competitors recommend, is it's a huge performance hit because that's why they're there. They're designed to work that way. So it does reduce variability though. So, but it eliminates how much CPU time you actually get to have and use. And then some concept of cache partitioning. There's some open source ways of doing that called cache coloring. There's you can cache locking some lock your application into cache once it's loaded. Although ARM is kind of getting rid of some of that user level cache capability. And then we have a patented way that we deal with that as well. Some of the cache locking and stuff, that's, you can lock ways, you can lock lines, and those kind of things. We looked at that, but, basically it's very specific to a particular processor architecture. So from an operating system company, it's not something we want to deal with. We want to have a very portable environment that works across all, is not limited to any of that. So what we came up with is an idea that's, partitioning cache per application. So you may hear and see a lot of processors with the ability to partition that shared cache at the core level. That seems to be at least what the hardware vendors are giving us to do, which is good, but that still leads you into the same thing you had with a single core model, where you still have cache competing in that, applications competing in that shared cache. So we went to a way to do it by application level. It's been certified. It's flying in single core environments and will soon be in multi-core environments as well. So what does that mean? Well, basically, it's the idea that you can take, think about cache is just accessed through memory. So if you had the way to take, let's look at the operating system first of all. It's a virtual address machine. It uses 4K pages. So if you can select the 4K pages that you want for your application such that the cache tags all match, so they all end up in the same area of cache, then you can partition the cache. And so basically, as simple as that sounds, we developed a way to do that where we can, through a configuration file, specify the mapping of the pages that get mapped to particular applications such that they end up in a shared cache area. So we have some white papers out like that if you want to explore the possibilities there. But it does two things. One, it partitions the cache per application. This all assumes that your applications will fit and you have enough shared cache and that. It's very configurable, so I got another slide that shows you the complexity that you can get into if you want. But it also, because it is dealing really with memory and how memory is allocated, in some of these SoCs where you have on-chip RAM and off-chip RAM, you can use it to select what apps you want in the on-chip RAM versus the off-chip RAM if you have speed concerns and that kind of thing, if you're using really small processors. We scale from the low-end E200 PowerPC cores all the way to the T series, so we end up with customers doing all kinds of things there. So just from a cache perspective, one of the things that this slide shows is we had one of our customers take this cache partitioning idea and run some tests with flight applications. And this gray band shows what their first run was. They basically had the L2, which was the last level cache in this particular processor, and no cache partitioning. So their worst case execution was around 100, and their best was close to 30, a little less than 30. And then they tried the experiment of turning L2 off, and sure enough, that decreased the variability of the task. But the best case was up around 60-something here. So you lost all this, performance. And then they did the L2 partitioning, and this was the band that they, worst case up here, best case. So the best case is a little higher, but your variability is really low, and you get, basically all this throughput back to do other stuff. So this was kind of the aha moment when we were designing this and saying, hey, we're onto something. This is one of the big offenders. And this actually is on a single core environment. So the multi-core environment's actually 3x the difference because of all the other things going on. So we looked at, and I know this is largely an open source community, so I'm sorry I'm putting patents up on the screen, but this kind of shows the kind of things you can do, because logically, if you have large data maps or radar arrays or something, you may not be able to separate all your apps into particular shared cache areas. But the idea is you can decide what stuff can work together the best way possible, and so you can group them any way that you would like. The other part of this from cache management is also managing your scheduling. So the idea is you want to be able to control what's running on a core opposite the core you're running on. So if you take the idea of, hey, I got a multi-core environment, now I can just use a hypervisor, I can throw this old software on there, run in by my safety critical app, and there'll be no effect. Well, that's just not true. There will be effect. There's going to be memory bus contentions, there's going to be memory controller contentions, there's all kinds of things. So the idea here is to control what you schedule across from each other. So maybe you have a memory-bound task on one core and you have an I/O-bound task on another core, or whatever. Or maybe you have cooperative tasks on different cores. We also, in doing this, we kind of put up a two-level scheduler. One's timing the windows. The other is running a scheduler. So you can run 653 partitions. You can run POSIX partitions, which happen to be RTEMS partitions. RTEMS is a partner with us in this environment, so we can run RTEMS. So you can take, if you have your space applications now that are all of a sudden the system needs some level of safety, avionics safety, or FAA's putting something on you, or the government, you can run your RTEMS software here as it is in a partition, and then add your 653 partitions wherever you need on different cores to make the system work together. So it's a way to move that existing software into a safety critical environment without a whole lot of work. Whatever that means, right? A whole lot of work. So, from a SMP or AMP, we like to call this a bounded multiprocessing. We also use fine-grained locking. I think that should be common. The kernel doesn't inject any interference in the system, but you obviously, as programmers, can decide to create that if you want. You can have threads or sharing memory pools and that kind of stuff. I'm going to try to speed up here because I think I'm running over, but we're fine? Okay. There's also the idea that safety nets I talked about. So in the idea, there's hardware nowadays that have these performance monitors in them. And you can set those performance monitors up to say, I only expect this many last level cache missings once my system is up and running. So you can put thresholds on that, and you can, if you hit those thresholds, then we put keys into the OS to say, hey, take that particular partition and shut him down for a cycle or until I tell him to turn it back up. You can basically have the operating system ability to, or you give the user control, I guess you'd call it the health monitor, or whatever overall monitoring system is saying, okay, we're going to shut this guy down for a minute, bring him back up when we feel like he's, or you may want to reboot him, or however you want to manage that. So that's kind of the safety nets that we put in, and there's hundreds of these depending on the types of architectures that you select. The last part of this is kind of a test setup that we built. When you start looking at cache and scheduling, it's really hard to show in a small footprint, so we tried to create a way to do that. So we created a test that has a worker process made up of 2 threads. It's filling a buffer, and then it checksums that buffer, and it's cooperating doing that. And then a trasher process that's basically just trying to trash all the memory at the same time. So looking at that, we put 4 different scenarios here: single core with cache partitioning, multi-core with no cache partitioning, multi-core with cache partitioning by core, and then by application. So you can see kind of how the results turned out. For detail on that, just kind of shows when you look at the single core, everything runs in order. So this gets done, that gets done. The trasher can't really affect it because it's not scheduled till it's a lower priority. So it's not even scheduled till after it. So that's pretty obvious. When you go to multi-core, you can have, if everything is running in the same memory pool, these guys, the writer and the checksummer can, the writer runs and then the checksummer runs. They can't really cooperate because they're scheduled on the same core. They have to wait till one's finished, do a context switch, and start up. The trasher is running on the other core, trying to interfere as much as it can, so it makes the number higher. It gets better if the trasher is actually in a different memory pool. So then it's not actually trashing the memory you're working on. It's just creating bus interference. So the not having to deal with the memory, but and messing with the cache makes it a little better. And then the best solution turns out that if you actually take and run the writer and the checksummer on different cores and have them in the same memory pool, and then have the trasher in a different memory pool, and it runs. And because they cooperate and they transition control, they actually do this faster than if they were on the same core. The reason one of these is, I like to say this, but the other is that, a lot of the guys look at this and, oh, it's contention. You've got 2 threads on different cores talking in the same memory pool. But yeah, they're working on the same data, so that makes sense. So that's my overall, basically, that's another one. But my overall basic thing I want to show is that, interference is not always a bad thing. You have multiple cores because you're trying to get a lot of work done, and sometimes they need to work together. And if you provide the way for them to work together in a certain manner, interference might be on your side, not working against you. So that's pretty much that. We provide this example in our development seat too with the example code, so you can play with it and mess around with it and see what happens. So that's me. I'm out in the RTEMS booth with those guys. If you want to talk later, any questions?
Yeah.
Hi. Did you use out-of-order instructions? Did you look at the performance of out-of-order instructions in all this?
We have, well, we looked at the problem of out-of-order instructions, and in the kernel manage that with locks to make sure that the instructions get done in order. It really doesn't become a problem unless you have two cores operating on the same piece of data, and you think that they're going to happen in a certain order. But the way these processors work, they reorder however. And so if you have to put in those window locks, I can't remember what the locks are called, but there's instructions to say, hey, I'm gonna make sure PowerPC EIO instructions or whatever to execute an order instruction. So that if you have a critical region, you have to deal with that. And we force that. We did it in the kernel, but we put that back on the users for application development. We give guidance to do it.
I was just going to add to that C++, when they added the standard locks and the threading, has had to come up with a memory model inside the language definition. And I think C11 had to do that as well for a defined behavior of how memory is actually supposed to work from the program's perspective, which was kind of loose. And I assume Ada did the same thing, because usually Ada's 10 years ahead of everybody else. But it's really a problem when you've got even on single core, you have to worry about the memory model for how it looks to the program. Things are a lot more complicated now. Yeah, there's all kinds of things the processors will do to you to change the way you think things are happening. Even writes, they'll like group up writes and reads, and things happen. It's really weird. All right, thank you.